Hello, I thought I might make a little update video about this electric wheelchair conversion project. I haven't actually done anything further, that is, I haven't actually physically put anything together, and I haven't really written any source code or any stuff like that, because I've had to spend quite a while investigating and learning and studying. Sometimes, unfortunately, you have to do that kind of thing. And also I'm waiting for some parts to arrive in the mail, so I couldn't really get much done even if I wanted to. But I thought I'd make a video just to, show you what I have discovered, because that'll probably need to be covered at some point anyway, so we might as well get it out of the way in this video, and then in the next video maybe make a little bit more actual progress. So if you wanted to see screwdrivers and spanners and getting physical with stuff, this is not going to be the video for you, so you might want to come back in the next video. Anyway, for the rest of us, let's see what this is all about. So at the end of the last video, you may recall that I said that the next step was to figure out what kind of messages were being transferred along the wires between the remote control unit and the ESC part of the wheelchair. And I said that I wasn't really sure what I was in for when it came to trying to decipher that. But fortunately, after probably just a few minutes of Google searching, I came across this. And this is video by Jim Connor. It's part 2 in a series that I, of course, binge watched as soon as I discovered them. And he has figured out basically what I'm trying to do. Not only that, but he has managed to obtain a document, PDF, that basically just explains the whole thing. So could have saved me a month of trial and error and frustration. And when I looked at the document to see how it was done, I'm not entirely sure that I could have actually figured that out. There's some weird stuff going on in there compared to what I'm used to when it comes to transferring messages across networks and stuff. But I'll just read a little bit of this comment here, because this kind of sums up quite well most of what we're about to look at in the rest of this video. So there is a wire that we noticed there was a plug with 4 connections on it, so that's the wire that he's talking about here. And he says the system uses an RS485 serial bus, so it's similar to RS232, which is just the typical UART connection that we're all familiar with from Arduino. And he said he did a bunch of work on decoding the signals, blah blah, and then somebody at Invacare, presumably, or Data Controls, or whatever the company is that makes this, the ESC unit, sent him a copy of something called the Shark Bus protocol so that he could finish the job. And that's the document that he says, if you send me a private message with the email address to send to, he'll reply to you and maybe give you that document if you ask nicely, which I did, and that's where I got the document from. But he said, though, he's not sure if the person at Invacare was supposed to be giving that information out. There was no non-disclosure agreement asked for or anything like that, but just so that we don't get that person into trouble, he asked me not to upload it to the web anywhere, and I won't be showing it to you in this video for that reason. But if you ask Jim nicely, he might give it to you too. Anyway, so another important point here. I was just using a little embedded Linux PC to send the messages to and from the bus. It worked pretty well until the CPU started to get bogged down. Then it would miss the very precise timing requirements of the Shark bus, and the controller would indicate an error that required that the wheelchair be turned off and on again. So that's something that we're hopefully not going to come across when we're using a microcontroller that doesn't have an operating system to make it get bogged down. Should be fine. So what is RS485? Well, I'm a little surprised that after tinkering around with Arduinos for a few years, I'd never heard of this. But there's RS485 and RS422, which are quite similar. And if you Google RS485, you'll probably come up with this page this link on the first page of results. And I found this to be quite good as a first introduction and just sort of an explanation of how it works. And to sum it up as quickly as I can, if you know how the regular UART connection works, you have a common ground wire, and then you have one wire which is being taken high and low with digital high and low, so it's going to 5 volts or to ground, and that will be sending the signal in one direction. And if you want to receive a signal back in the other direction, you'll have another one, and the other end of the connection will be taking that one high and low, and you can listen to it. But in either case, you need a common ground between the two endpoints so that they can measure what it means to be 5 volts and what it means to be 0 or ground. And RS485 is a bit different in that instead of having a common ground that stays at the same level and one wire going up and down, both of the wires go up and down, and more importantly they cross over, so that in one state one wire will be more positive than the other, and in the other state, so the other states being 0 or 1, digital 0 or 1, they'll cross over so that the other wire will be higher than the first one, if that kind of makes sense. So both wires are being changed in voltage, so that in one direction it's sort of pushing current through, let's say it's pushing current to the right through B and pulling it back through A, and in the other state, when it's 0, let's say it's pulling it through B and pushing it through A. And you can see I'm not sure if this page goes over the advantages of that, but it's much more resistant to noise and interference from outside situations, so it's more commonly used in heavy industrial machinery and stuff like that. And it can also go much further, up to about 800 meters, I think, with a 5-volt signal, which is pretty amazing. And there was something else as well. Oh, faster. You can get up to, don't know if it says on here, but you can go much faster than you can with a normal RS-232 connection. Oh, well, I'll let you read that. But anyway, so they've chosen RS-485 because it's much more robust, basically. And because you don't need a common ground, or this A wire and B wire, they kind of function as a reference to each other. That's why it's called a differential fashion like that. You just need these two wires to carry the signal. And another important distinction is mentioned here. In RS-485, each driver or each endpoint can be switched off, allowing multiple units to send data over a single pair of wires. So that means that instead of having a dedicated RX and TX line like we do with the UART connections for a typical Arduino RS-232 connection, you just need these two wires, and you can connect together many different endpoints, and they can all talk as long as they take turns. They don't all talk at the same time, that would not work, but they can take turns as long as they're timed properly. They'll be able to talk to each other. So a little bit more investigation led me to one of these things, which is thankfully very cheap, and this will let you plug in an RS-485 connection there, though, so that's the two wires going out to the other RS-485 device on that end. And on this end we have basically what is, you can treat this as if it was a normal UART connection, so your Arduino can talk to this end. So I ordered a few of these, but they haven't arrived yet. That's one of the things I'm waiting for. As far as which pins were which on my wheelchair thing, I found this PDF, which I think is a publicly available one, so I can show you that. And right at the end of this there was quite a handy little diagram which showed a picture of all the connections and pinouts. There's actually two styles here. I think this one at the top is an older one, maybe. Anyway, this one here is the one that I have, because it's got this 12-pin thing there. So this is the connection going to the control unit that, as we mentioned before, has just 4 wires. And if we look on the next page, it says here which of these pins is which. So that's battery negative and positive, and then we've got the communication bus high and low. So this high and low are the two wires that we use for the RS-485 connection. Battery negative and positive obviously is coming to the hand control unit to power it. And I guess this also lets power come in from the charger as well when you plug in the battery charger. So from that it was pretty simple to figure out what was going on this plug, because you can just use a continuity tester on your multimeter to see which one of these comes out where on here. So this is just a picture that I made for myself for future reference, just in case I forget. So these are obviously just what we saw in that diagram, and this is where they go to on here. I took this picture. I didn't really need this one, because afterwards I realized that there's a 45-degree bevel here that makes sure you can't plug it in the wrong way. So as far as the direction of the plug, looking at this is enough, but I just wanted to take this photo here so that I could see this little icon is only on one side, and I washed out this picture, increased the gamma quite a bit so that I could actually see it. So this is actually not necessary. Anyway, this is how the pins are laid out. So that made it quite simple to do some quick tests like this, just by plugging in a few screws, or just screwing in a few self-tapping screws. I'll have to do something a little bit better than this in the future. I think I might be able to use my CNC machine to make a little thing in the same shape as this, so that I can just slot it into that multiple connector system that's on the bottom of the wheelchair. But anyway, just for now, this was one easy way to just put some alligator clips on and look at it with the oscilloscope, which is what I'll show you next. Here's a screenshot from my oscilloscope showing the traces for the bus high and bus low pins, and the blue one is actually bus high. In the resting state it's held low at almost 0 volts, and the bus low in the inactive state is at 5 volts just about. It's kind of funny that the document that Jim got, it basically describes RS485, but I don't think it ever mentions the name RS485 anywhere. It just describes it in full, almost. It's kind of strange. But anyway, everything that I saw on my scope matches up exactly with the description in the document. So you can see that when we actually get some signals happening, the voltages on these traces will switch, so that the low one, oh, this is bus high really, isn't it? Whatever. The one that's normally low will go up to about 4 volts. The one that's normally at 5 volts will come down to about 1 volts. And that's how the signals work. So this is how it obtains its robustness. And the document says that it should be a 38,400 baud speed. And looking at the signals here, we can see this is a 1-bit signal here. Just from looking at it from a while, you can see that this is the smallest width of pulse that ever happens. And at 38K, that should be 26 microseconds. And this is 100 microseconds per division. It's about a quarter of a division, so it's matching up quite well. Now remember that this is a bus, so even though we have 2 separate traces here, 2 separate wires, they are not one person talking and another person talking. They're just the same signal. And if other people want to, or not people, but other devices on the bus want to talk, they have to wait their turn. So the timing of everything has to be very carefully managed. Let's take a small step back and we'll look at this here. This is Jim Connor's GitHub, and he's uploaded the source code that he was using in his videos. If you go and watch them, which you probably should if you want to know how far he's got with his project. So he implemented it in Python, which I presume he's a bit more comfortable with, and then there's also C re-implementation when he discovered it needed to go a little bit faster, I think was generally the reason for that. And there's a file here called SACUC, which contains most of the goodies. So this thing seems to be called Shark Bus, which I presume is some kind of an acronym for something there, but I don't know what this shark is all about. Anyway, to be honest, I didn't really look too much at most of this code because I was planning to implement it myself on Arduino, and now that I have that document, it didn't seem too complicated. So I just looked at this SACU file a little bit, and you can see here that he has the function that when it detects that a packet has been received from somebody else on the bus, he just checks. Most of the message types can be ignored, but then there's this one and this one that needs to be responded to, and needs to be responded to very quickly, otherwise the next person or the next module or next device on the bus will start talking and overwrite our message. So it has to be very, very carefully timed. And the timing of these packets is explained in the document that Jim managed to get hold of, which I think I will just show you this one little part of, because it will save me from drawing this diagram myself. So there's basically frames that take place, and one frame is 20 milliseconds in total, and each device or module on the bus takes turn in talking, shall we say. And to figure out what these SR and SPM things are, let me just go back. So this is SR, that's the Shark Bus remote. Shark Bus power module is SPM. And then Shark Bus attendant control unit. This is the interesting part. So what this is this thing sticks up on the back of the wheelchair, so somebody pushing it from behind can override the control that's down there on the armrest. So if the patient is asleep or unconscious or something like that, or crazy maybe, I don't know, they can flick this switch, and then this joystick will take precedence over the one down there on the armrest. So this is the thing that we need to get our Arduino or whatever it is that we're using to communicate with the chair. We need to emulate this SACU. So that's what the SACU.c file was in Jim's code before. So now we know what these are: Shark Bus remote, Shark Bus power module, and Shark Bus attendant attendant control unit. Now you can see that these are all taking turns to have their say, and it has to be done in this 20 millisecond time frame. This here is a transmission finished packet. So basically this says that the SharkBus remote is done with what it wanted to say, and then the SharkBus power module can say something, and then it puts another transmission finished there. So this is what Jim was saying about if the timing wasn't perfectly right, if you don't get your SACU message out on the bus before this point here, the SharkBus remote will start talking over you. And I'll just read a little bit from the PDF here. It says, the SharkBus remote shall initiate the transfer by sending its general information packet. It follows this with other packets, such as HHP data, which I don't know what that is, as required. Finally, it sends a transmit finished byte. Then the SPM responds with its own general... That's basically what I just told you, isn't it? Okay, so you can probably see how it works from there. And the more I looked at this PDF, the more I began to think that I probably would not have been able to figure this out myself. Not because it's super complicated, but just because it's quite different to other stuff that I have dealt with in the past for sending transmissions over networks and communication lines. And this is a good example of how I typically do things, and this is how the U-Blocks or UBX protocol works as well. You have a couple of characters that signify the beginning of a packet, and they'll be fixed. In this case, it's like this micro symbol and then a B for microblocks or U-Blocks or whatever you want to call it. And then you have the information and length and some stuff like that, and then the packet data, and then you'll have a checksum at the end. So you just look in the stream for these 2 bytes here, or however many bytes are in the header that you're looking for. Then you read in the rest of this, and then check if the CRC matches, and then you have your packet. But there's some really weird stuff going on with this SharkBus protocol, and I will read out a little bit more of this. Let me just find it. Here we go. So I'm just going to read this little bit from the PDF. It says, while the data format is 8 bits, bit 7 in each byte shall be used to indicate the first byte of a packet. Bit 7 shall be 0 for the first byte of a packet, and 1 for all other bytes. So instead of having a set header kind of set of bytes like this, all you need to do to figure out if a byte is the first byte of a packet is check if bit 7 is 0 or not. And on one hand, that's pretty simple, makes it easy to find the header bytes of a packet. But it's a bit strange because that means that by taking away essentially the data that's in that bit, because every other byte in the packet, that bit has to be 1, so that we don't think that any of these other bytes here are part of the header. So what you've done by doing that is that you've effectively thrown away half of your bandwidth. Seems very strange, and something that I never would have expected. Anyway, the rest of the structure is kind of similar. There's like a type here, and then you have the content, and then you have, I think it's just 1 byte for a parity check. So that much is kind of similar, although there are, again, some other strange things. Let me just read a little bit more from this document. The first or start byte of a packet defines its type and the length of the data it contains. The type is in bits 0 to 3, and the length is in bits 6 to 4. This allows for 16 packet types, each containing up to 8 bytes of data. So what they've done is, in this microblocks, you have 1 byte to say which message type it is. So that gives you 256, I guess, possible message types. And then you have 1 byte for the, actually 2 bytes to say what type of message it is there. So that's heaps. And then the length is contained in another 2 bytes. So that gives you, how many is, 500? 2 bytes. 2 to the power of 16. And then you've got another 2 to the power of 16 possibilities for the length of the packet. Whereas the SharkBus protocol, you've got 4 bits total for each of these. So as it said, you can only have 16 packet types, and each packet can only contain 8 bytes of data. They've really sort of limited themselves a lot, and I just don't really see the need for it. Perhaps it's because the speed that this stuff is running at 38,400 baud, they didn't want to go any faster than that because it started to get little bit sketchy about whether the information would be received properly. I don't know. Maybe that's why. And they wanted to, at 20 milliseconds, this is going to be 50 frames per second, which seems like more than enough. So it's just really kind of strange. I don't know why they've made it like this. They've really limited their options for expandability, it seems. How many frames per second would be enough to drive a wheelchair? I'd say about 20. Should be enough. I don't know. Anyway, it's very weird, and suffice to say, I don't think I would have figured this out, to be honest, if I didn't have that PDF. But anyway, since I do have that document, I wanted to check that it was still current, because when I turn my wheelchair on, the screen shows me something a little bit different to what the document was written for, and I was just hoping that nothing had changed. So what I realized I could do is, even if I don't have a proper RS485 converter thingammy, one of these signals here is just a normal RS232, like just a normal UART signal. And it's actually this yellow one here, so this is Shark Bus Low. So I could actually just connect to this and just listen to the bus with an Arduino and, you know, print out some debugging information and check that it was all making sense. So that's what I did next. I did not use the blue. Obviously it would need to be inverted if I wanted to use that. But there was also another problem, which is just about the only fly in the ointment at the moment. And that is that when you turn the wheelchair on, and also when you switch it back on at the remote after it's been off for a while, this voltage here goes up to full battery voltage. So that's going to be about 25 volts or so. And if I just go to my next tab here, the Max 485 chip, so this here, is what is on this. So that's that thing there. And that's what's... it's just sort of a comparator, I think. Is there a diagram? Oh, never mind. Anyway, the point is, the absolute maximum ratings for this thing are... I think the important one is this one here, receiver input voltage. So this can only go up to 12.5 volts. But my wheelchair, the power module, when it wakes up, is going to take this line to 25 volts or so. So even when I get one of these, I don't know what to do. I don't think... These are cheap enough that I don't mind breaking them to just, you know, connect up one and see what happens. See if it breaks, it doesn't really matter. But it could mean that I need to get some sort of a protection circuit in place on the receiving, on the bus high pin there, just so that I can, you know, make it work at all. So that is a hurdle that I have not managed to get across. And let me just show you a screenshot that I took of the oscilloscope when that happens. Here we go. So this happens when the chair powers up, like when you plug the battery in, and it also happens if you turn the remote control thing off and then turn it on again. And it's quite short. It's only 300 milliseconds, but it is quite strong. So let me just zoom in a bit there. So this is 10 volts per division. So you can see the normal signals that we were looking at before are down here. They're about 5 volts. And then just for a short time, this bus high goes really high. And this is what I'm worried about. Even if it's short, I think it's long enough that it would damage that little chip. So not totally sure what to do about that. I looked into voltage overprotection, and there was some sort of a cheap trick you can do with a Zener diode and a resistor. But I think what that would do is it would interfere with this signal. This needs to go to 25 volts. And I think the way a Zener diode works is it just breaks down and it becomes an open circuit. A closed circuit. Essentially that would be pulling this to ground, and I don't think it would work, because then the power module would not see this 25 volt pulse, and it wouldn't be able to, it wouldn't know that it should wake up. Anyway, I haven't figured out what to do about that, but that seems to be the only problem that is likely to, you know, put a spanner in the works at this point. Anyway, back to this normal signal. So as long as I don't use that blue trace, as long as I just plug in my Arduino to this other Shark Bus Low side, it's not, this one doesn't go up to 25 volts at any time. So this one is safe to use. So that's what I've been using. And let me just have a little rearrange of my windows here. So I have my thing there that's on, and my Arduino is connected to that. I'm just going to show you right at the top what's going on here. So I have a serial begin. This is at 115K. This is going to the serial monitor. And then I have a software serial running at 38.4, and that's going to the Arduino, or this is going, these pins, pin 2 here is connected up to the there, bus low. So that's what is happening here. And I found that if I made this serial slower, it would mess things up, because my serial monitor needs to be running faster than this one, I think, so that we don't start getting bogged down. But anyway, if we look at the serial monitor there, is this running? Okay, you can't really see it too well because it's just printing out 128 over and over. And I've just put in a bunch of stuff here to look for the, the start of a packet, and then put the bytes into an array, and then check that the checksum matches and everything. It's all a bit of a mess, so I won't upload this just yet because it doesn't do anything. But right here I have a message function that just sort of tries to print out some information, and all it's doing at the moment is it's printing out packet 4 of this packet, or the 4th byte of that packet, I should say. And when I turn the remote off, it requests a power down from the power module, and that will change 1 bit in this packet. So it's not much to look at, but we can at least look at that. So keep your eye on here, and actually it'll probably be around about here, because it'll scroll up and then the scrolling will stop. So let me just turn this off. And if you weren't very careful about watching this, you might have missed it, but there's 132. It changed from 128 to 132 for a little bit. So that means that 1 more bit has been set in that packet. And then after a while, the power module responded with the OK to shut down, and then it shuts down. So this remote doesn't shut down without permission from the power module. I think that's how it works. Anyway, you can see it's also not scrolling anymore. So everything's shut down. The bus is quiet. Now, when I turn it on, we'll see one other message that I'm printing out is the power-up information. It'll print out the year and the month that it was, the version of the software maybe, I'm not sure what the year and month is of, and then a version number and a bit flag with some capabilities. So let's have a look at that as well. So turn it on, and you see it started scrolling again. So I'm just going to stop it scrolling and go back to wherever that was here. For some reason there's 2 packets showing up there, but anyway, we can see that the year was 2005, the month was September, software version is 1, and then bit flag 15, which I think is pretty much all the bits set. So this, this thing can do all the capabilities. Not exactly sure. We have to look in the document to see what each bit of that capabilities bit flag means. But anyway, it's all making sense. Of course, at this point, I cannot actually send any information on this bus. I'm just sort of listening to it and printing out what the Arduino sees. But still, that's a good first step. It means that I can at least understand what's going on from these other modules that are already there, which is good to begin with. So when my RS485 converter thingies arrive, that's these ones here, I'll try connecting them up and sending some information on this bus just to see what happens. But I'm not sure that it's going to work, and one of the reasons is that the what's this thing? SACU. When everything's sending those power-up packets, like we just saw the Shark remote sent its power-up packet that we saw, this SACU thing is supposed to send a power-up information packet as well to announce its presence in the system. And I think if it doesn't do that, actually, I don't really know. If it doesn't do that, maybe it's not going to get listened to thereafter. But if that's the case, it could be a problem, because this pulse also shows up when it's turned on. So I can't just connect my Arduino after everything's powered up and run it. I'll need to have my Arduino connected while this big pulse is happening in order for it to work. at least in the future I will anyway. Maybe for testing it would be okay to connect it here. But when it's all set up and running in real application, it's going to have to be able to withstand this pulse somehow. So I'm not really sure how I'm going to get around that one at this point. So that little bit of coding that we saw just before is about the only thing that I can show you as far as demos go. It wasn't really much. It's not the only coding I've been done. I have been doing some experiments, mostly with Node.js, and trying to get Node.js to talk to a serial port, which turns out was actually quite easy. So the reason why I was doing that would need to be explained. I'll get to it in the next slide, but this is the first arrangement. I'm just sort of, pipe dreaming here, since I don't have anything else to show you. But this is how I'll arrange things for the first revision, and this should be no problem because it's very similar to stuff that I've done in the past for flying, quadcopters and stuff. The only difference is that there's an RS-485 here, and there is, of course, that fly in the ointment with the 25-volt pulse, which is going to be a problem. But apart from that, I don't see any issues with this situation. So this should be enough to drive the thing around, remote control, and if you put a FPV camera on it, then, of course, you can drive it FPV. I have just a normal FPV camera, a CMOS camera, that I'm thinking to put on here and drive it, use that to look at through for the first iteration. After that, now, if this thing is going to be a bit more interesting than just a radio control car, it's going to need some kind of autonomy. And as I mentioned in my first video, I would like it to be able to drive back home if it was out somewhere and it lost radio control. So that's going to need some kind of breadcrumb following procedure, which is going to require a little bit more memory, a little bit more processing power. And another thing that I would really like to have is the ability to just look and see on a map where it is, and also to tell it where to go just by clicking somewhere on a map. So that's where the Node.js comes in, because Node, or JavaScript in general, is the easiest way to use Google Maps, basically. I have also tried to do this with Qt, and Qt being cross-platform is a great way to make a cross-platform app. I'm just keeping in the back of my mind that other people might actually want to use some of this stuff in the future, perhaps. I don't know. Probably not, but just good to try and make things as cross-platform as possible. So Qt is good like that, but it's a bit awkward to get a map into it, I've found, a Google map rather. And JavaScript, on the other hand, is very, very simple. So I thought, what if I could just make something in JavaScript that could also do serial connections? And one way to do that is with the Chrome app, and that's also very easy. I tried that. It was like falling off a log. Easy. The trouble with that, though, is that Chrome is actually going to be dropping support for Chrome apps early next year, which is not a problem if you just keep an older version of the browser around and use that, but that's kind of a pain in the butt. So I thought I would try using Node.js and make this into a server. I guess if this is a server, this part here is going to be running the Google map in JavaScript, isn't it? Oh yeah. Well, at some point I just discovered how easy it was to make a server out of Node.js, so I thought, well, Node.js is going to be running the server here. Anyway, so this side of things is kind of similar, except for instead of an Arduino, I'll most likely be using an STM32 development board because it has a lot more processing power. They're not too expensive, but they are way a big step up in capabilities. And I found one that has a MAX 485 chip on board, and it also has an SD card, which is probably going to be quite handy. And it also has a header for plugging in an NRF24 module directly. Not really necessary. I mean, you can always just connect that up to some SPI pins anyway, but it's just kind of handy to have that header ready to plug it in, I suppose. So this side of it will be kind of the same. And then over here, thinking about setting this NRF24 up with the big Yagi antenna and putting it somewhere sort of semi-permanently outside, pointing down to the far end of the farm. And as such, so this whole section here is going to be semi-permanent. It's just going to be set up and running all the time. And as such, I didn't want to tie up one of my laptop computers with that. Basically, that's the reason I am thinking about Raspberry Pi or Odroid because I don't mind having them tied up permanently because I don't really use them that often, but I do use my laptops for other things. I don't actually have a Raspberry Pi. I do have an Odroid, which is why I'm going to try it with Odroid first. And Odroid runs Ubuntu 16.04, and that's what I was testing Node.js on. So yeah, everything there should work quite well. And I have also in the past used Odroid with a SPI connection to NRF24. So that much I've done. Raspberry Pi is also pretty simple to work with NRF24, I think. Yeah, so then at this point, all you need is sort of some JavaScript that can run a Google map and maybe with some buttons to turn some lights off or switch on, return to home or something like that. And all that stuff is pretty easy. I've done that before as well. Nice thing about that is it could be multiple clients, so you could have it running on your Android as well. Or you could look at it on your Android, I should say. Alright, so it's all a bit of a pipe dream, but something like this might eventuate after just getting the basics up and running, but we're looking at a little bit longer term there. Now, one other idea I had, actually just stumbled across this today actually, these IP cameras, these are just something that I sort of scroll past when I'm looking at the latest things on Banggood. There's quite a lot of them there, and some of them are fairly reasonably priced. And they have Wi-Fi on them quite often as well. And this got me thinking about maybe something like this. Actually, that's not a Wi-Fi one. But if I just go back to my plan, this is my my third idea, and this is going to make things a little bit simpler at the back end. See, now we don't have NRF24 L01. So one of the problems with this is it's packetized. So there's no, if you want to send a stream of data, you have to manage that stream yourself, and it's a bit of a pain to do that. So it's all just going to have to be packets, and they're 32-byte packets. So you can't fit too much in one single message. And if you want, like I say, if you want large messages, you're going to have to disassemble it here and then reassemble it on the other side. And the other thing is that to get a bidirectional communication, you're going to have to use the ACK payload coming back from here. And the whole thing's, it works, I've done it before, but it's just sort of a bit of a headache to set up, and you can run into problems quite often. So what I thought is, if I could simplify it all by doing this, it might be a little bit easier. So in this situation, you'd have one of those IP cameras on there, so you would not need any 5.8 gigahertz radio signals anywhere. You'd have a better camera, because a lot of those cameras are 720p or even 1080p, and they also quite often integrate some illumination for their IR camera, so you can use them at night as well. Plus, a lot of them are also waterproof to begin with. So in many ways, they're a lot better camera to be using when you're outside roaming around, and probably at night sometimes as well. Plus, if they have Wi-Fi on them, and I stick my big Yagi antenna onto my Wi-Fi router at home, I can probably still use the Wi-Fi inside the house with my laptop and my Androids and stuff, because it's quite close, but it should send the signal pretty far down the end of the farm where the rover can still hear it. So I'm not actually thinking to use the integrated Wi-Fi, so that's why I haven't drawn a connection from here to here. What I'm thinking to do is get a second router. I actually have one that I was using in Japan, and when I moved back to New Zealand and set up my internet here, they give you a router when you sign up for the internet access, so I didn't need my one that I had in Japan, but I can hopefully use this one to set up a Wi-Fi bridge of sorts, so that this router is just sort of a client on the network of this router, and then the Raspberry Pi or the Odroid will be out there, and it can still run that server, and that server will be able to be accessed by my desktop computer and my tablets or my laptops at home through this route. And because it's running over Wi-Fi, it won't have that sort of annoyance that the NRF24 has with those packets and ACK payloads and stuff like that. And it's using TCP, so it's all, you know, if there's errors, it will be resent, and it's basically, what do you call it? reliable connection. So that would take a lot of the headaches away. Yeah, so I'm really liking this. Actually, I might just try and skip over to this. But the big sort of challenge here is getting the router set up. Getting this router set up to pass information backwards and forwards properly. But I do like the idea that you don't need a separate 5.8 gigahertz sort of analog video signal coming back here, because one of the things I didn't draw in on here is video being returned. So you're going to need some other kind of a screen and some other antenna and some other wiring and all that. You're going to need a whole lot more wiring and sort of stuff to get visuals back at this point. And most likely you won't be able to see it on your computer screen. You'll have to look at it on like a FPV monitor or something like that. So it won't all be in one place and tidy. Whereas if you do it like this, my map will be in one tab of my browser, and most likely the IP camera view will be in another tab of my browser. So I can just sort of line up my browser tabs on my screen however I like, and I'll be looking at it all on my desktop computer. Yeah, more pipe dreams, eh? We'll see how it goes, but if anybody has any ideas about that, about this system in particular, I'm quite excited. Like I say, I only came up with this idea a few hours ago. That's why I'm still sort of buzzing about it. But yeah, if anybody has set up a router as a client of another router just to sort of relay information through, yeah, let me know. And I think I may have to replace the firmware on my router, but I looked up the model name and it seems to be compatible, so we'll see how that goes. Hopefully I don't need to do that, but anyway, it's probably time to wrap up this video, isn't it? So yeah, I guess before I finish, I've said this before, but if anybody has any ideas about what to do about, where's it gone? About that, yeah, let me know. So signal line over voltage protection is the Google search that I've found the most help for. And there was actually something called a, let me see, what was it called? This is the one that I was looking at. It's called MAX 4505, and it's a signal line protector. Protects from over voltage faults up to 36 volts with power on, or 40 volts with the power off. The problem with this though is that I was looking at these specs here, and it says electrical characteristics are power supply range, so it needs 9 volts to run this thing. And the way it works is it clamps the voltage on the signal line to this, whatever it's being powered with. So if you power it with 15 volts, it won't let that signal line go above 15 volts. The trouble is the minimum it's going to accept to run is 9 volts. So if I'm trying to protect a 5 volt signal line, then I don't want to give it 9 volts. I mean, maybe I'm reading this wrong. I don't know. If anybody knows a little bit more about how this thing works, maybe you could give me some tips on that too. The other option is another thing. Let me just find that one. Alright, this is the last thing to look at, I promise. So this is called a LT1785, and it's basically an RS485 transceiver like the MAX 485, but this one is already fault protected up to 60 volts. So I guess this would be the silver bullet for the problem that I'm having. If I can get hold of one of these somewhere, I might try and do that. But anyway, I think I better just shut up for now, and let's see if in the next video we can make some more, physical sort of actual progress and see something happening. But for now, thank you for watching. See you next time.